Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This is yet another video in a series on optimization problems for differential calculus. You should have already watched my video on the tactic that I have for optimizing or dealing with optimizing problems in calculus, and you might have already watched my videos on maximizing areas and volumes, all that fun stuff. Here in this one, we're just going to focus on a single problem, which is maximizing an angle. It's one of my favorite problems, honestly. In this problem, we're going to go ahead and reference this picture or this image here. Where should the point P be chosen on this line segment from A to B so as to maximize the angle theta? All right, so again, we have this point P that is right here. And what we want to do is move that point up or down so that theta is maximized. Theta will change as you move P. In this case here, we're going to allow A, the side A here, to be 4. Let's put that in there. And side B to be 7. And side C to be 11. So we'll go ahead and write all that stuff in. Let me go ahead and adjust my pen. It was like slightly broken there. And C is side C is 11 units. So round your answer to 2 decimal places and write your answer in terms of how far P should be from A. All right, so write your answer in terms of how far P should be from A. So this we'll call a distance of X there. All right. So there's a lot of things to think about. Our answer should be written in terms of X, that distance that P is from A. That's what they told us to do. And this is a very unique problem in that maximizing this angle theta is similar to a completely different question. So, well, not a completely, a related question, I should say. A lot of people will spend some time trying to figure out how to maximize that angle. They'll try to create a relationship between that angle and the given information. Some people will draw a line. Let me see if I could do it here. Yep, I can. I'm sorry about the screen. For some reason this morning, my internet is terrible. So some people will try to create a line here and figure out maybe there's some way to figure out the distance of that line and maybe use the law of cosines here and maximize the angle that way. There's a lot of different ways that people will go about trying this. I've used this problem for years, and I would say that the best tactic, honestly, is to recognize that if you have maximized this angle theta here, you essentially have minimized the remaining angles, the supplementary angles, or the supplement angles. Well, supplementary angles is fine. So I'm going to call this angle here theta A, and well, A is probably a bad letter to use. No, that's a great letter actually. It's opposite side A. So we'll call this theta sub A, and we'll call this angle down here theta sub C. And maximizing the angle theta is the same thing as minimizing the sum of theta A and theta C. So we're going to ask the alternative question. How do you minimize the sum of the angles theta A and theta C? That's actually a better question in this case. So there we have it, minimize theta A plus theta C. Now we just need to figure out how to write theta A and theta sub C in terms of X, because that's how we want our answer, in terms of X, which is a distance that P is from A. Well, if the total distance from A to B is 7, then the distance from P to B is 7 minus x. And now I can relate these angles. For example, theta A is related to the known side of 4 and the sort of known side of 7 minus x by tangent. So off to the right, or left, sorry, here, I'm going to go ahead and write the tangent of theta sub A is going to equal 4 over 7 minus x. Also, using the same logic, theta sub C is going to be, the tangent of theta sub C, sorry, is going to equal 11 over x. So there's another relationship there that relates these angles to x. Now remember what we want to do. We want to minimize theta A plus theta sub C. And unfortunately right now we have these in terms of tangent of theta sub A and tangent of theta sub C. We would like to write these only as theta sub A and theta sub C. Well, that's just taking the tangent inverse. I want to give you a heads up that you could totally do this because remember, the tangent inverse will return an angle that is acute. It's an acute angle between, well, in this case, it'll return an acute angle between a literal acute angle between 0 and 90 degrees. Normally, the tangent inverse would return an angle between negative 90 degrees and positive 90 degrees. However, because theta sub A is going to be an acute angle, and the tangent inverse we're taking is going to be of a positive ratio, the tangent inverse will return a proper angle between 0 degrees and 90 degrees. So that's perfect. So I'm going to use a different color here. Blue is what I wanted to use. And I'll say that theta sub A is therefore equal to the tangent inverse of 4 over 7 minus x. Again, just want to reiterate, the inverse tangent or arctangent will always return angles between negative 90 degrees and positive 90 degrees, depending upon whether or not its argument is negative or positive. In this case, distances are always positive, so its argument for the tangent inverse here will always return a quadrant 1 angle which is an angle between 0 and 90 degrees. And likewise, theta sub C is going to be the tangent inverse of 11 over x, and again, that will be an acute angle. So really what we want to minimize is that's the sum of those tangents. And what I'm going to do is go ahead and say, how do I want to say this? I don't want to call that angle theta because it's not, right? That angle is actually pi minus theta. So maybe I'll just, that's what I'll call it, pi minus theta. That's really what it is. But I don't really want to do that either. Now I'm thinking about it. I will call this angle alpha. That's fine. So we have alpha as a function of x is equal to, remember alpha is just theta A plus theta C, or theta sub A plus theta sub C. And that is going to be tangent inverse of 4 over 7 minus x plus tangent inverse of 11 over x. Our goal is to minimize alpha, and therefore that will maximize theta in our picture over there. So alpha is just the supplement of theta. All right, now we are going to go ahead and find the critical numbers of alpha. Alpha prime is going to be, and that, by the way, alpha prime, when I say alpha prime, I really mean the derivative of alpha with respect to x, because alpha is a function of x. The derivative of a tangent inverse, recall, is 1 over 1 plus its argument squared. It's one of the most important derivatives to remember as you enter into Calculus 2. So it's going to be 1 over 1 plus the argument squared. The argument of this first tangent inverse is 4 over 7 minus x. And then, by the chain rule, you take the derivative of that 4 over 7 minus x. That I'm going to treat as a quotient. So the derivative of the numerator is 0 minus the numerator times the derivative of the denominator, which is a -1, all over that denominator squared. And then we are going to add to that the derivative of the tangent inverse of 11 over x. Again, it's 1 over 1 plus that argument squared. The argument being 11 over x, and the derivative of 11 over x is a -11 over x squared. That's by the chain rule. And I'm going to go ahead and just clean this up before I set it equal to 0, just because, well, it's kind of nice to do. You can see this first product is going to be 4 over this 7. When I say this, I mean this guy right here. This 7 minus x quantity squared will distribute to both of the terms in that denominator. And in the first term, it'll just be a beautiful 7 minus x being squared. In the second term, the 7 minus x squared in the numerator will cancel with that 7 minus x squared in the denominator. So you'll just end up with a 4 squared or 16. Very nice. Plus, and the same thing will happen in the second term, except now that I see that, it's going to be a net minus 11 over x squared plus 11 squared, which is 121. And now I can go ahead and set this derivative equal to 0. You might be wondering why I'm not saying when is this derivative undefined. It's because that derivative is never undefined. It always exists because of the fact that these are sums of non-negative numbers, and one of them being positive. So these denominators are always positive. All right, so alpha prime is equal to 0 when the first fraction is equal to the second fraction, right? So when 4 over the quantity 7 minus x being squared plus 16 is equal to 11 over x squared plus 121. And this is just going to be a gnarly algebra problem. And most of them, actually, you've probably seen in this video series, most of these optimization problems end up just testing your algebra skills over and over and over again. It's kind of a trudge through algebra when you're doing optimization problems, honestly. It's just how it is. So you get 4 times the quantity x squared plus 121 is equal to 11 times the quantity 7 minus x being squared plus 16. And this is a good reason why I know some of my colleagues in mathematics education kind of just say, and then you can solve the rest. And I understand why they do that. It's because there's just a ton of little algebra here. But I also know that the weakest part for students in a calculus class, their weaknesses always stem from prerequisite material, not calculus. They're somewhat okay with the calculus. It's the algebra and trig that kill them. All right, I'm going to do a quick distribution. I'll actually pause for the distribution. At this point, you can see why I paused, because it's just a lot of computation there. I'm going to shove everything over to the right-hand side. And again, I'll pause the video for this. We get down to this guy right here, and there's no point in trying to factor this for a couple reasons. One, the numbers are just horrendous, but also this is a real problem, and the answers are likely not going to be pretty. So I'm going to immediately just jump right into the quadratic formula, which is something I generally would not tell a student to do. But when you're in optimization, all the answers tend to be terrible. So I'm going to just jump right into the quadratic formula. And I get down to these two answers. X is roughly equal to 20.4 or X is equal to 1.6. This is actually a really good problem because you need to check the reality of those answers. Is it realistic for X to be 20.4? And the answer to that is heck no. The side length B there is only 7 units long, so X cannot be 20.4, but it sure can be 1.6. So that's what we're going to assume is, or not assume, that is the actual answer. So I'm going to throw out the extraneous answer and go up to the top here. We have minimized the sum of those two highlighted angles, theta sub A and theta sub C. Therefore, we have maximized the angle theta. So write your answer in terms of how far P should be from A. Well, P should be, I'll write it this way. P should be 1.6 units away from A to maximize theta. Really good problem, and really showcases how you have to sometimes use alternative methods rather than straightforward maximizing what they tell you. It might help to think about minimizing something related. That's all I have for this video. I'll see you in the next video for a talk about how we can do maximization of revenue in a non-calculus way.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.